And in sample estimates, again, some basic statistics. So if the model is IID model, independently identically distributed model, then we assume that basically return is the expected mean plus some white noise. And again, similarly, we have covariance matrix, which is basically in this case, this is the covariance matrix sigma. And in this case, simple estimators will be the sample estimators. So in this case, if this is the IID process, then basically sample mean will be, if we have t observations, then the returns at each t time step, average of these returns at each t time step will be the sample mean. And that will be the sample mean that we'll use in the portfolio. And another thing is the sample covariance matrix. And again, the covariance is, again, return minus estimated mean, sample mean, times return minus, again, the sample mean transpose. And this is multiplied and summed over each time step, where time is from 1 to the t. And then it's divided by 1, divided by t minus 1. And in this case, it's t minus 1 instead of 1 divided by t, because we want to get an unbiased estimator. And this is the rule, if you remember from the statistics, we divide by y minus t, because in this case, the estimator is unbiased. And again, another estimator in this case is the least square. So in this case, in the least square will give us basically the sample mean and the sample covariance that we are interested in. Assume that we are having returns. So in this case, we have the return here, and return t is, RT is return at t, and we assume that we are trying to minimize its difference with respect to the mean of the return. And then this minimization, once we sum up with an optimal solution for this least square estimate, then the optimal solution to this problem will be the sample mean, where we are basically summing up the returns at each t time step and then dividing by t. And again, the sample covariance of the residuals, which is basically RT minus sample estimate, will be the covariance matrix. In this case, our covariance is basically the covariance of the residuals, covariance of the residuals, which is not explained by the returns, and returns minus the estimated mean return. And this is the least square estimate. And another estimate is maximum likelihood estimate. Again, it's used as high as the least square error estimate. And in this case, we assume that, again, the returns follow a Gaussian distribution, and they are independently identically distributed. So in this case, basically, this is a multivariate Gaussian distribution when 1 divided by 2 pi n, and determinant of the sigma, which is basically, this is the determinant of sigma, which is the covariance matrix itself. And in the exponentiation part, we have 1 minus 2 and minus 1 divided by 2. Again, R minus mean transpose, inverse of this covariance matrix, R minus, again, mean. So this is multivariate Gaussian. Multivariate Gaussian. And in this case, basically, this is in order to come up with maximum likelihood estimator, we assume that they follow a Gaussian distribution, and these are the parameters. And again, the maximum likelihood estimator is basically minimizing the minus log. So it's basically maximizing the multiplications, which becomes minimizing the minus log times the maximum likelihood estimator, or the Gaussian distribution for each returns. And if we take basically logarithm, then we come up with an expression as you see here, which is basically depends on the logarithm of the determinant, and as well as the expression that you have seen here. And again, for multivariate Gaussian distribution, so for least square, we haven't assumed anything about the distribution of the RT. But if you assume that the RT is distributed maximum likelihood, then we write the expression in the log expression, and then we take its derivative and set to 0 in order to find the optimal values, because in the optimal values, its derivative is equal to 0. And if we take the derivative and set to 0, then we find basically mean estimate in these returns is same as the least square. So this is same as the least square estimate. However, the sample covariance or the estimated covariance is slightly different than the least square. Instead of dividing by 1, instead of dividing by t minus 1, we are now dividing by t. So this is the difference with respect to least square. Difference with respect to least squares estimate. And that's the difference between the maximum likelihood estimator and the least square estimator.